Example, Justin Case is sitting at rest on a skateboard with a 4-kilogram bowling ball in front of him on the ground. The combined mass of Justin and the skateboard is 65 kilograms. He pushes on the bowling ball with an average force of 8 newtons for 1 second. Assume friction is negligible. So we're going to draw a momentum diagram which has the basic parts of the before event and after pictures. And then it has initial momentum of system, change in momentum of system, and final momentum of system. So starting with our pictures, the before picture should have velocities of the object. So here's the skateboard with Justin sitting on it. And here is the bowling ball. I guess he needs long enough arms to reach the bowling ball. We better make a large bowling ball. So there's the bowling ball. And the mass of the bowling ball is 4 kilograms. And the mass of these objects is 65 kilograms. So on your before picture you need to have the velocities. And it looks like at the beginning of the problem they're at rest, so nothing is moving. The after picture also should have velocities. And afterwards, he's pushing on the ball. So afterwards, the ball is going to be going this way, which I'm going to call that the velocity final of the ball. And Justin is probably going to be going this way. So maybe we should call this velocity of the ball final, and this velocity of Justin final. Then the event picture should show the forces on each object. So go ahead and pause the video and draw your forces and then check back. So during the collision, or during the pushing of the ball, there's his super long arm, there's going to be a force of Justin on the ball, force of Justin on the ball. And then by Newton's third law, there would be an equal and opposite force of the ball on Justin, force of the ball on Justin. And then there's going to be a force of gravity on the ball and a normal force. And same thing for Justin and the skateboard, a normal force and a force of gravity. Okay, let's look at what our system is going to be. For the first part of the problem, the system is going to be the ball. Is there a net external force on the system? So the first step is to look at what your system is. My system is the ball. So any forces caused by objects outside of the ball would be external forces. So this is an external force, this is an external force, and this is an external force. So all the forces on the ball are external forces. But we're asked for the net external force, so we need to add these together. The normal force and force of gravity will cancel out. So when I add these three forces, the net force is just the force of Justin on the ball. So is there a net external force? Yes. Does the momentum of the system change? Yes. And on the previous page of these notes, make sure you read that sentence down at the bottom, which says that the momentum of the system will change if there is a net external force. So that is the condition. Another homework assignment you have this week will ask you that question. This is a really important key idea. When there is a net external force on the system, the momentum will change. Okay, let's continue on. And it doesn't even say here actually what we need to find, so I will just help you with what we're going to be finding. In fact, we're going to do it a lot like we did the previous example. We're just going to find everything we can along the way. But specifically, we want to get to finding out the final velocity of the ball afterwards. So let's see what we know already. Initial momentum of the system. Is this something I can calculate? I know the mass before, and I know the velocity of the ball. So I can find the initial momentum, which is 0. And then I can represent that here. So draw 4 kilograms but it doesn't have any height because it has no velocity. Change in momentum, we'll come back to that. Let me see if I know anything here. Final momentum, mass times the final velocity, or you could put the velocity of the ball final. I know the mass, but I don't know the velocity of the ball, so I can't calculate anything here yet. So let's take a look at the change in momentum of the system. Change in momentum is equal to the impulse. It's caused by this force that acts over a period of time. So I think we have some force and time information. We have a force of 8 newtons and we have a time of 1 second. And let me think about the force. What's the direction of my force? Always think about the direction of your force. That is positive. So positive 8 newtons times 1 second gives me an impulse of 8 newton seconds. And that is my change in momentum. So this is useful because initial momentum plus change in momentum equals final momentum. The initial momentum was 0, because we found that over here. The change in momentum is 8 newton seconds or kilogram meters per second, and that's equal to the final momentum. Now that we know the final momentum, we can calculate the final velocity of the ball. So the final momentum is 8 newton seconds. The mass was 4 kilograms. So solving that, we can see that the final velocity of the ball is equal to 2 meters per second. And that's positive, so that's telling us that the ball is moving to the right at 2 meters per second. And so afterwards we can draw this, has the same mass, 4 kilograms, but the velocity is 2. So afterwards the momentum looks like this, has a momentum of 8. In this next part, we're going to use a different system. This time the system will be Justin and the skateboard. And the net external force, let's see, is there a net external force? So let's go back now and look at our diagram. So now, if the system is Justin and the skateboard, which would be right here, what are the external forces? Well, normal force, that's from the ground, so that's from outside the system. The earth is outside the system, so this is an external force, and the ball is outside the system of Justin and the skateboard. So these are all external forces. Normal force and force of gravity cancel out, so net external force would be the force of the ball on Justin and the skateboard. So net external force, yes. Does momentum change? Yes. Whenever there is a net external force, the momentum will change. So I would suggest you go ahead and work out this section and then check your work with the rest of the video. And what you want to do is calculate, initial momentum, change in momentum, final momentum, and the final velocity.
Okay, so initial momentum of the system is going to be mass times velocity. The mass is 65 kilograms for Justin and the skateboard. Initial velocity is 0, so initial momentum is 0. So this is not going to be to scale very much, but I'll try to show that it's a larger mass and that it has a velocity of 0, so 0 momentum. Final momentum is going to be mass times final velocity. I could put an initial velocity I over here. Mass times final velocity, so 65 kilograms, but I don't know the final velocity and I don't know the final momentum, so I can't do anything else with that. Let's see if I can find the change in momentum. Well, I know that he pushed on the ball with a force of 8 newtons for 1 second. But what was the force on him? Well, because he was interacting with the ball, the amount of force with which he pushes on the ball is the same as the force that the ball pushes on him. That's a Newton's third law interaction force pair. So these two forces, the force of Justin on the ball and the force of the ball on Justin and the skateboard, those have equal magnitudes. So if this one was 8 newtons, this one is also 8 newtons. But here's where you have to be really careful. You have to put in the negative sign to show the direction of that force. So back to here. We're trying to find the change in momentum of the system, which is Justin and the skateboard. So the net external force on Justin and the skateboard is -8 newtons. And the time is 1 second. Whenever you have an interaction, if one object pushes on the other one for 1 second, then the first object also experiences the force for 1 second. It's not possible to touch the other object longer than it touches you. So -8 newton seconds is our change in momentum. This is going to enable me now to find the final momentum, because I know the initial momentum is 0. Change in momentum is -8. So the final momentum must be equal to -8. And now I can use this over here. And calculating that, we get -0.12 meters per second. Okay, the last step is to draw the momentum diagram. So here's my object of mass 65. And this is a very small velocity. So using somewhat the same scale that I did up here for the ball, if this is -2 and this is -1, -1/10 would just be really tiny. But make sure it's below because this is a negative velocity. Okay, so what we notice here, just to summarize, is that the ball during this interaction had a change in momentum of +8. Interestingly, the other objects in the system, Justin and the skateboard, had a change in momentum of -8. So notice that, and we'll follow up with that next week in class. The other thing to notice is that even though they both experienced the same force, the ball ended up with a larger velocity afterwards than Justin and the skateboard. And that shouldn't be too surprising because the masses were so different.